Welcome back to ShubhCode. Today is episode 22 of the Apex interview questions series. Topic: Dynamic Apex and Callable Interface Masterclass. Unlocking extensible architectures, reflection, and plug-and-play Apex design. These are the questions that real interviewers at top Salesforce firms ask. Let's go. Here are the questions we're answering today. Understanding dynamic Apex reflection and Type.forName, then, the power of the System.Callable interface then, building a decoupled plugin architecture then, dynamic parameter passing and map serialization then, FLS, CRUD, and security injection risks in dynamic Apex then, handling runtime exceptions and graceful fallbacks then, unit testing dynamic modules and mocking plugins then, real-world enterprise use case, dynamic payment gateway engine. Stay for the last one, it's the most important. Let me explain this simply. Unlocking extensible architectures, reflection, and plug-and-play Apex design. Dynamic Apex reflection allows your code to discover and instantiate classes at runtime without compile time dependencies. When you write, type T equals Type.forName, payment processor, Salesforce resolves the class name dynamically from a string variable. You can then invoke, object equals t.newInstance, to cast it to an interface or object. A common gotcha happens with managed packages where you must pass the namespace signature, Type.forName, namespace, class name. If the string name is typed incorrectly or points to a non-existent class, Type.forName returns null, causing a fatal null pointer exception on newInstance. Introduced to standardized dynamic execution, the System.Callable interface contains a single method signature, object call, string action, map string, object args. Unlike traditional custom Apex interfaces, System.Callable allows loosely coupled cross-package communication without requiring shared dependency modules. For instance, you cast your dynamic object using callable plugin equals callable t.newInstance and execute plugin.call process refund args map. This completely decouples your core architecture from implementation details. The main edge case is type safety because arguments and return values are untyped object maps, requiring defensive casting. To build an enterprise dynamic engine, pair callable with custom metadata types storing implementation class names. Suppose your org supports multiple calculation engines, you store class names like Tier 1 tax engine in custom metadata records. Your core engine reads this metadata and dynamically executes, callable engine equals, callable, Type.forName, meta.class_name_c.newInstance. This pattern allows developers to add new features simply by deploying a new class and adding a metadata record, completely bypassing core code modifications. A best practice here is enforcing an abstract base class or default fallback engine if metadata points to an invalid implementation. Passing complex S-objects and custom data models through callable requires structured map payloads. You would write, map string, object args equals new map string, object, record ID equals record ID, account equals ACC, before invoking call, execute, args. Inside the dynamic class, safely extract values using explicit casts, account ACC equals, account, args.get, account. A major gotcha occurs when passing primitive types across namespace boundaries. JSON serialization via JSON.deserialize untyped can be used as a boundary bridge. Always validate mandatory keys with, if, args.contains key, record ID, throw new illegal argument exception, missing parameter, to prevent silent execution bugs. Dynamic code execution introduces severe security considerations if input class names originate from untrusted user input. If an attacker controls the class string passed to Type.forName, they could instantiate unintended internal system classes. Always restrict dynamic targets using an explicit whitelist or by querying trusted custom metadata records. Furthermore, dynamic Apex classes execute in the context they define. If your dynamically called class uses without sharing, it overrides core security constraints. Ensure dynamically instantiated modules explicitly declare with sharing and perform FLS checks using security.strip inaccessible before processing sensitive record updates. Dynamic code execution can fail in multiple ways, including class instantiation failures, missing action handlers, or runtime logic exceptions. To build a resilient architecture, wrap dynamic instantiation in strict try-catch blocks. You would write, try, callable plugin equals, callable, t.newInstance, plugin.call, action, args, catch, exception e, logger.logError, e, return fallback execution, args. Catching generic system.type exception handles illegal interface casts, while system.nullPointer exception catches missing classes. A best practice is publishing a platform event or logging to a custom object whenever a dynamic plugin fails, ensuring full system visibility. Unit testing. Dynamic Apex frameworks require specialized strategies to ensure code coverage and mock missing runtime implementations. Since dynamic classes might not exist in sandbox or test environments, leverage test variable injection or mock plugin registers. In your test class, you can register a test stub class implementing system, callable to simulate success and error responses. You write, dynamic engine.register mock, Stripe plugin, new Stripe mock callable, during test execution. Always write explicit unit tests for both valid class names, and negative scenarios where Type.forName returns null, ensuring your fallback and exception handling routines achieve 100% test coverage. Let me walk you through a production enterprise use case, a global multi-gateway payment processing engine. Depending on the customer country, the system dynamically routes transactions to Stripe, PayPal, or Adyen. A custom metadata record maps country codes like US or UK to specific processor Apex classes. The orchestrator calls type t equals type.forName, gateway meta.class_name__c, callable gateway equals, callable, t.newInstance, gateway.call, charge, payload. If a new payment provider is added next month, developers deploy the new provider class and metadata row without modifying or retesting the core checkout system, demonstrating true enterprise architectural scalability. Quick recap before you go. Leverage Type.forName, with system, callable to build plug-and-play, decoupled enterprise Apex architectures. Always implement strict null checks and fallback handlers when instantiating dynamic types to avoid production NPEs. Protect dynamic execution paths against injection vulnerabilities by whitelisting classes against custom metadata. Design testable dynamic engines using mock registration patterns to achieve robust code coverage for all execution paths. These answers will set you apart in your next Salesforce interview. Like this video if it helped. It takes 2 seconds and helps the channel a lot. Next up, Salesforce Apex Interview EP23, Advanced Garbage Collection, Heap Memory Optimization and LDV String Buffer Patterns. See you tomorrow.